Have you ever stopped and wondered what you're really made of? I mean, not just skin and bone, but the absolute fundamental stuff. Well, today, we're taking a journey to the very core of reality. We're going on a tour inside the atom.
It's a huge question, right? One that people have been asking for thousands of years. But everything, from the phone in your hand to the stars in the sky, it all comes down to this one unbelievably tiny, incredibly powerful little structure. And that's exactly what we're here to unpack.
So let's get ready. We're going to shrink ourselves down and take a guided tour. We're diving right inside the atom to see how it's all put together and, maybe more importantly, why that specific structure is the reason for, well, everything. All right, our first stop on the tour is the basic blueprint. This is where we meet the three key players, the fundamental particles that make up every single atom in the entire universe. Okay, take a look at these numbers. You've got your protons, which are positive, and your neutrons, which have no charge. Notice they both have a relative mass of 1. But then look at the electron. It's got that negative charge, but its mass is tiny. It's almost 2,000 times lighter. So, here's the key takeaway. Almost all the mass of an atom is crammed into its super dense center. And this paints the perfect picture of an atom's layout. You have this incredibly dense, positively charged nucleus made of those heavy protons and neutrons. And then, buzzing all around it, you have this cloud of those super lightweight negative electrons. So what keeps them from just zipping off into space? It's that classic rule, opposites attract. The positive nucleus holds on to the negative electrons with a powerful electrostatic force. Okay, moving on. Let's talk about identity. What actually makes a carbon atom carbon, and not, say, an oxygen atom or a gold atom? Well, the secret? It's all in the nucleus.
The best way to think about this is like an ID card for the atom. The most important number on that card, the one that defines everything, is the proton number. You'll also hear it called the atomic number. This number is non-negotiable. If an atom has 6 protons, it is carbon, period. End of story. The other number, the nucleon or mass number, just tells you the total weight of the nucleus. You just add up the protons and the neutrons. So what happens if you play around with the number of neutrons? Well, you get something called an isotope. Because the proton number hasn't changed, it's still the exact same element. It just has a different mass. They're kind of like chemical twins. They look and act the same, but one is just a little bit heavier than the other.
And this is the perfect example. Carbon-12 and carbon-14. They both have 6 protons, so they are both without a doubt carbon. They'll react chemically in the exact same ways. But you can see carbon-14 has 2 extra neutrons. That makes it heavier, and it turns out it also makes it radioactive. This is the exact isotope we use for carbon dating. Pretty cool, right? Okay, we've covered the nucleus. Now we're heading to what I think is the most fascinating part of the atom, the world of the electrons. Now, this is not some simple system like planets orbiting the sun. Oh no, this is a world with some very strict and frankly very weird rules. You can almost picture it like a bizarre apartment building. The main floors of the building are the principal shells. These are the main energy levels. Then each floor is divided into different types of apartments, which we call subshells. And finally, inside those apartments are the individual rooms or orbitals, and that's where you'll actually find the electrons hanging out. So let's start on the first floor, the one closest to that nucleus at the center. This is principal shell number 1. It's a pretty small floor. It can only hold a maximum of 2 electrons. But as we go up to the second floor, principal shell number 2, things get a little more spacious. There's more room up here, so it can hold up to 8 electrons. You can start to see the pattern, right? The farther away we get from the center, the more electrons can fit. And now for the final and most important rule of our electron apartment building. Each individual room, each orbital, can hold a maximum of 2 electrons. And here's the catch. They can only share a room if they have opposite spins. You can think of it like one spinning up and one spinning down. It's a fundamental rule of the quantum world.
So why do we care about all these shells and orbitals and spins? Why does it matter? Because this incredibly precise structure is what gives an atom its personality. It dictates exactly how it will behave and react with other atoms. And we can actually measure this personality by seeing how much energy it takes to rip an electron away.
And that measurement has a name, ionization energy. I like to call it getaway energy. It's the price you have to pay, the amount of energy you need to pull one electron completely away from its atom. If that energy cost is high, it means the atom holds its electrons really tightly. If the cost is low, it gives them up pretty easily.
So what determines that price? Well, it's mainly three things. First, the nuclear charge. The more positive protons you have in the nucleus, the stronger the pull on the electrons. Second, the distance. Electrons that are closer to the nucleus are way harder to remove. And finally, something called shielding. Inner layers of electrons can actually block some of the nucleus's pull from the outer electrons, making them easier to pluck off.
Okay, that's all the theory. But what does this actually look like in practice? What happens when we try to pull electrons one by one from a real atom like sodium?
Now, just look at this chart. To remove the first electron from sodium, it takes a relatively small amount of energy. That's that short bar on the left. But then, try to remove a second electron and look at that massive jump. That huge spike in energy is telling us something really important. It's telling us we just broke into a full, stable inner shell, and the atom is putting up a serious fight to stop us.
And this, right here, is where it all clicks into place. These huge jumps in energy, they're not just random data points. They are clues. They're like a secret code that lets us figure out an atom's identity and even predict where it belongs on the periodic table.
What's so amazing is how predictable this pattern is. For sodium, that big jump happens after we remove just one electron. That tells us it has one outer electron, putting it in group 1. For magnesium, the big jump is after the second electron, which means it belongs in group 2. For aluminum, you guessed it, the jump is after the third. The energy data literally reveals the number of electrons in the outer shell. It perfectly confirms our whole model of the atom.
And that's really the big idea to take away from our tour today. The structure of the atom isn't just some abstract theory in a textbook. It's the fundamental code, the operating system, that dictates the behavior of our entire universe, from the simplest chemical reaction to the unbelievable complexity of life itself. The rules we just explored are the very rules that built everything around you. And it really makes you wonder, what other secrets are still locked away inside?